Guys. Um, so this is a video on just an extra practice problem. I thought was kind of a nice one. Just relating motions of things. And I thought I would solve it kind of in the language would have used in physics one. And then I also worked it out with vector notation. So right, so that's just really what I wanted to do. Just kind of work through this slowly and go from there. Okay, so here's the following situation. We have a pulley. Notice I'm going to get fancy here. I discovered that I have shapes. Okay, so I'm going to have a pulley here, and I'm going to have a smaller pulley over here, and I'm going to have let's see, do I have well, I'll just draw this one. All right, and then I'm going to have a rope. Change the color of the rope to be black. So I'm going to have a rope which goes over the top and wraps around, and we're going to imagine there's a block C. And we're going to imagine that it rolls without slipping. So there's no slipping. And furthermore, we're going to imagine that initially, we're going to say that the velocity of C is down. And we're going to assume that the acceleration is up. Okay? And I'm going to have some numbers and things to give you. Change the diameter a little bit. So here I'm going to say that the radius is 600 millimeters. And over here, I'm going to say that the radius is 400 millimeters. Okay, 400 millimeters. Other numbers that I have to give you. So I'm going to tell you the initial velocity of C is going to equal 1,000 millimeters per second down. So I'm going to say that's negative 1,000 millimeters per second down. And I'm going to say the acceleration is a constant 100 millimeters per second squared. And since it's going to accelerate upwards, we're going to say that that's a positive acceleration. All right, so here's our goal. Our goal is to determine the following quantities. I think the slightly wider font is a little easier to read. Okay, so I want following. A, the initial acceleration. Oh, sorry, I should have marked this out. There's a point right here. We're going to call that point D. All right. And just for reference, this wheel is called A. Oh. And this wheel is called B. Okay. So I have wheels A and B. I have a point on the edge of wheel A, which I'm going to call D, and I have a block called C. All right, so what do I want? I want the initial velocity of, the initial acceleration of point D. So acceleration of point D at time equals 0. And you might be saying, well, wait a minute. I said that the acceleration of c was constant, so why isn't the acceleration of point D constant? And what you have to remember is that D lives on a circle, which means it has both tangential and centripetal acceleration, radial acceleration, or normal acceleration. And as the speed increases, the radial component of acceleration will increase in magnitude. It's change in magnitude. All right. Then I want B, second thing, I want the acceleration at D at time equals 8 seconds, and C, the number of revolutions, that pulley A turns, oh, can't write, after or in 10 seconds. Okay, so that's the goal. In 10 seconds, so we want to find those three things. We want to find the acceleration at point D at time 0. We want to find the acceleration at point D after 8 seconds, and then let's find the number of turns that wheel A goes through after 10 seconds. And we're assuming no slipping. That makes the analysis much easier. Okay. All right, so I've done this here a couple of ways. I've done it once in the language of physics 1, and then I'm going to redo it in the language of cross products and that. And of course, you get the same answer. So I just wanted you to see how that would proceed. Some of you guys did really well in physics 1 on rotational motion. So you can, if you know that stuff well enough and you kind of think about it, you can use that same approach here. Okay, so some general thoughts. If there's no slipping, then each point must have the same tangential velocity, each point on each pulley, and it also must be the same as the velocity of C. So in particular, we know that V at D, at least as a magnitude, must be the same as the magnitude of the velocity at C. Now, it comes to minus signs, we have to be a little bit more careful. All right. Furthermore, looking at my diagram, I see that both pulleys will move, at least initially, in a, let's look at that. So if the initial velocity is down, then we're going to have that both are moving clockwise, and then the accelerations are kind of going to cause them to accelerate in a counterclockwise fashion. All right. Furthermore, because this is a planar motion, that means that when it comes time to write omega and alpha as vectors, that they're going to point along the axis of rotation, which is perpendicular to the screen. Okay, so just remember that some of those vectors are going to point out of the screen. We'll call that the z direction. All right. Okay, so let's take a physics 1 approach and go from there. And so the first thing I would have is, from physics 1, I would say that that the velocity, I guess the tangential speed, at D has to be the same as the speed of the moving block. So I'm going to say then that well, and because the acceleration is constant, I can write that at least as a magnitude as the acceleration of c times t plus vc initial, and then take the absolute value of that. That just comes from the kinematic equations we all know are true when the acceleration is constant. Now, because the point D is on the edge of a circle, I can relate that to an angular velocity. So I can say that v tangent at D equals, well, it'd be r times omega. So it'd be the radius at D times omega at D. Now I have to be a little careful here. I have a speed on the left-hand side, but omega could be positive or negative. And from the diagram, or from the picture, I was told that initially the mass was going to go down, which means initially circle D, or pulley D, is going to rotate clockwise, which means at least initially omega will come out negative. Okay, so we got to be a little careful of that. But so maybe I should just put in absolute values right here, and that's certainly a safe statement. All right, and similarly, I would have that R similarly, I could say that the tangential acceleration at D equals RD times alpha for wheel A. Right, and that's by the same kind of logic here. And well, that's okay because alpha is positive, so I haven't made a mistake there. And finally, what I know is that at least the magnitude of A radial, or in dynamics, the book likes to call that the normal direction sometimes. The radial component of acceleration, or centripetal acceleration, is v squared over r. So that's going to be v tan squared, the minus signs don't matter, over r at point D. And then that's simply going to be, well, you can just use the above expressions to get that. Okay, so let's go through these things then. So those are the kind of the formulas I have in my mind that we would have discussed, the way we would have discussed it in Physics 1. All right, so let's go through the math a little bit more carefully. The acceleration at D at time 0, so question A, at time equals 0, the acceleration equals a tangential acceleration plus a radial acceleration. And the tangential direction, if you go back, if you're standing at point D, then and it's spinning, sorry, and then the acceleration that is going to point straight up, the tangential acceleration, sorry, oh, take it back. Yes, that's right. The tangential acceleration is going to point straight up. It's going to be in the positive y direction. The radial acceleration at point D is going to be in the negative x direction. So if I wanted to write out the total acceleration at point D, then I would say it is 100 millimeters per second squared times y hat, that's the tangential component. And then I'm going to get minus, and then I have the initial speed is 1,000 millimeters per second. Hold on, did I get the wrong? Make sure I have the correct numbers. I write the right number on the problem. Yes, that's right. The initial speed was, in fact, 1,000 millimeters a second. So that was okay. Had a moment of panic there. All right. Times, so that's the, okay, that's the initial velocity or speed, squared, divided by the radius. And the radius at D was 600 millimeters. So this is nothing other than V squared over R. Okay, so that's just the usual familiar formula for the radial component of acceleration, but I'm going to have to put in an x hat because it points to the left there. All right, so if you type in some numbers and we get the following result, we get that this is 100 millimeters per second squared y hat minus 166, whatever, 6.7 millimeters per second squared x hat. Okay, so that's the first answer. All right. The next thing we wanted to find was to find the acceleration at D when time equals 8 seconds. So we're just going to proceed, but now we're going to use the fact that it's really the same kind of problem, but now we use the fact that the velocity has increased because of the acceleration of the falling mass. And we have a number for that, so we can do that. The acceleration was 100 millimeters per second in the positive direction. Okay, so that means everywhere I have velocity, I can write the velocity equals 100. I'm going to drop the units here, times time, which will be 8 seconds. That's the acceleration times time minus the initial velocity, or sorry, plus the initial velocity, which is negative, which was 1,000 millimeters per second. Okay. And so I'm going to plug that in, and I'm going to do the same thing. So I'm going to say that the acceleration, the tangential acceleration remains the same. So that's still 100 millimeters per second squared in the y hat direction. This is D, minus, and then I'm going to have 100 times 8 seconds minus 1,000 millimeters per second squared x hat. That gives me the acceleration, or that's going to be, oh, be careful. This is the velocity. I have to square that, and I have to divide by the radius, which is still 600 millimeters. Okay. Again, that's nothing other than v squared over r at time equals 8 seconds. All right, you type in some numbers and you get 100 y hat minus 66.7 x hat millimeters per second squared. Okay, so that's the acceleration after 8 seconds at point D. Finally, we want to find the number of revolutions. And the number of revolutions, well, there are different ways you can go about it. Well, there are lots of ways you can find it. So the way I went about it was I first found alpha, And then I found omega as a function of time, and I found the initial omega, and I integrated to find delta theta. The other way you could do it would be to just find the change in y, or sorry, the change in height of the mass. And since you know that the wheel A spins without slipping, that the arc length that wheel A must turn through must equal the distance that the mass C has fallen through. They all amount to the same thing. It's just shuffling. You either multiply and divide by the radius at the beginning or at the end, but it's all completely equivalent. So I wrote it out here one way, so I'm going to write it the same way. It may not be the easiest or the shortest way, but that's okay. Okay, so alpha is going to be, this is alpha for wheel A, is going to be 100 millimeters per second squared divided by the radius of wheel A, which would be 600 millimeters. So that's going to come to 0.1667 radians per second squared. And the initial angular velocity is going to be, so initially it rotates clockwise, so I'm going to have a negative initial velocity, and that's just going to be the tangential speed, which we know, divided by the radius, and so you end up with 1.667 radians per second. Using the fact that alpha is constant, you can use kinematic equations to find omega as a function of time equals, so it should be alpha times t plus omega naught, which is nothing other than 0.1667 times time minus 1.667, and the units will come out as radians per second. Type it all in. Great. Next up, we need to find delta theta. So delta theta is simply going to be, well, there are lots of ways you can do that. We have the time, so I suppose we could do that, use that method. So we're going to say the change in theta is the initial angular velocity times time plus 1/2 alpha times the time squared. And I've got all the numbers there, so you just type them all in, and you're going to get negative 8.34 radians, which corresponds to negative 1.32 revolutions. Okay, so I'm going to pause for just a moment, and then I'll come back and kind of rewrite this with fancy vector notation, but you'll see it's really not any harder. Okay, so I want to rework the same problem, and I'm going to use vector notation to kind of work all these things out, and you'll see the same answer pop out. So, all right, so just remember here, the answer that we arrived at, well, remember, you can flip back and see the previous answers. Okay, so this is going to be, I don't know what to call this. We'll call this the fancy pants way. Fancy pants way. All right, so I'll go a little faster here because you've already seen all the numbers. The following is going to be true. We're going to have the initial velocity at point D. So the initial velocity at point D is going to be, if you think about it, initially it's moving clockwise, which means the initial velocity is down, which means it's minus 1,000 millimeters per second y hat, and the vector, the relative vector from of D relative to A is going to be 600 millimeters x hat. Similarly, I can write omega of wheel A as a vector at the start is negative 1.667 radians per second, and it would be z hat. And alpha is going to be, for wheel A, is going to be 0.667 z hat, and it would be positive, as we discussed before. 0.1667, sorry. All right. Now, in the last video, or in the lecture video, I said that that the general formula then for the acceleration at point D would be alpha cross R D relative to A, and then it would be plus omega, cross the quantity omega cross R D relative to A. Okay, so we've got everything in vector form. We just have to work out these cross products. So it's useful to remember, note, when you have planar motion, you don't normally just get random vectors times random vectors. You have a lot, because the rotational omega and alpha point in the z direction, you end up with z hat crossed a lot of unit vectors. So it's kind of nice to have them written down. So remember, x hat cross y hat equals z hat. Y hat cross z hat equals x hat. And z hat cross x hat equals y hat. And then if you switch them, you get a minus sign, because cross products are antisymmetric. All right, so using those, we can write out, so the answer for part A, so at t equals 0, the acceleration at point D is going to be, well, I'll just write it out again. It's going to be alpha cross RD relative to A plus omega cross RD relative to A, and dropping in the little pieces that we just wrote down on the previous slide, I can write this as 0.1667. I'm going to pull out the common factors, the scalars, times 600, and then it'll come out as millimeters per second, times z hat cross x hat, because alpha goes in the z direction and r points in the x direction. Hold on, I'm gonna make sure I didn't get this wrong. Yeah, so this would be the position of D relative to the center of the disk, so it would be positive 600. Yep, that's all correct. And then I have to work out plus, for the radial component, I get minus 1.667 squared, because each of the omegas, this omega gives me a scalar factor, this omega gives me a scalar factor, and then this r gives me a radius factor, and then I have to deal with some unit vector stuff. So these are my two omega factors, and then the radius would give me an extra factor of 600 millimeters. And then I have to work out z coming from this omega cross z hat coming from the second omega cross r, or cross x hat. Oh. Which comes from the radius vector. Okay, so if you think about it, okay, so imagine you've got your xy coordinate system, which I guess for you are like this. Try to mirror it for you. So I've got x and y, and if that's x and y, x and y, then let's think about it. X, y, then z is going to be into your eye. Got that right. So if I look at it, I'm trying to look at it like you guys look at it. So I'd have x, y, z. Yeah, so that's right. So x, y, and then z is into your eye. Okay? I have to use my left hand, so I've got to be a little careful. Okay, so z cross x, z cross starts in your eye, turns to the side, is going to point in the y direction. So inside the parentheses, this piece gives me a y hat, or I can just use the ones I just wrote them down in the previous slide. I'm sorry, lose my mind. All right, so they give me a y hat, and then when I cross it with z hat, that whole thing is going to give me z hat cross y hat is negative x hat. This is good because the centripetal acceleration go towards the center of wheel A, so that's in the right direction. You multiply all those out. Oh, and this piece is nothing other than a y hat. So in the end, I get that the acceleration equals 100 millimeters per second squared y hat minus 1667 millimeters per second squared x hat, which is the result we had before doing it the physics 1 approach. Way back a couple slides. There you go. Same answer as we would have done in physics 1. Okay. Let's go ahead and repeat the analysis. It's really the same basic idea. For part B, I'm going to say that omega vector as a function of time is the integral of alpha vector as a function of time dt plus omega initial vector, but that's nothing other than 0.1667 t minus 1.667 radians per second z hat. And if I plug in numbers, that's just going to give me at 8 seconds, I'm going to get omega vector at 8 seconds equals minus 0.333 radians per second z hat. All right. So I go through the same process, and I'm going to get the acceleration at d at 8 seconds equals alpha cross radius d relative to a minus omega cross alpha. It's really the same process as we just had. It's just, sorry, not alpha, r hat, r vector. It's really the same process. It's just now we evaluate everything at 8 seconds, not at time 0. So I just have different numbers, but the method is the same. So this first factor doesn't change because alpha is constant, and this just gives me the same 100 millimeters per second squared y hat. The second factor gives me, so minus, and I get two factors of omega, and hold on a second here. Did I put an extra minus? I think I put an extra minus in there. I have an extra minus sign. This should have been a plus here, which makes this a plus. And then I'm going to get 0.333 squared, 1 from each factor of omega, times 600. And then the unit vector stuff is going to be exactly the same as before, because omega still points in the x, or sorry, in the z direction. So that'll be times negative x hat. So make sure I did my math earlier correctly. I'm going to get 0.333 squared times 600. Yeah, it's the same. I think I just had a transcription error in my notes. So this gives me 100 millimeters per second squared y hat minus 66.7 millimeters per second squared x hat. Very good. And to find the change in theta, well, that's just, or the number of revolutions, that's a scalar quantity. So vector stuff doesn't really change the analysis at all on that. So I'm not going to redo that one. You would proceed exactly the same way. Okay, so hopefully you can see how this sort of complicated looking formula that we had last time reproduces the same analysis we would have done with physics 1. It's just for planar motion, you really have a choice. When you get to 3D, this vector notation wins out. But in 2D, you can do it if you want, but you'll get the same answer. Okay.